this video is the first part of the lecture, double integrals over general regions. And we are going to see how to compute the double integral. How to compute double integral of a surface f of x and y dA over the region R, where R is any general region. So we have something like this. We have x-axis, y-axis, and then z-axis. We have a surface, something like this one, f of x and y, and we're gonna find the double integral of that over a general region R. And as we talked about this before, double integral of f over R basically gives us the volume of a solid that lives here, that is bounded below by the region R in the xy plane, above by the function f, and on the sides depend on the shape of the R. So how can we find this volume of the solid that lives here? We need to take slices. How do we do that? Well, let me first write this. We take slices. We basically slice the solid above R and below F by parallel planes. Parallel planes. Okay, so just assume that we have, let me just make this one a little bigger. I'm gonna raise the y-axis and make it just a little bigger. So this is y-axis. So I'm gonna basically slice the solid that I have in here by a parallel plane to the y-axis. So let's make the slice something like this. I have just a plane like this. This is a plane at x naught. Okay, so x equals to x naught. It's that. And okay, I just basically slice this, and as you see on this slice, I can call it S of x naught. Okay, so let S of x be the area of a slice by plane parallel to y, z plane. And it is still between R and the function fxy. Okay, and equation of the plane is x equals to x naught. Okay, let's S of x naught to be the area of this slice. Okay, then the sum of all these areas gives us the volume of the solid in here. But basically, we need the region between every two slices, two parallel slices. So if we have just the volume in here, and then we just slice it, and if we slice it one more time, we add up the volume, we add up the areas of the slices. We need to basically find the little area, the little volume that is between any two slices. Just assume that this is one slice, this is another slice, okay? And then we need to find basically this volume in here between the two slices. But the volume that is between these two planes is just basically Sx dx, the thickness, let's call it dx. Now we are taking the limit, so we have more and more slices that are very, very close to each other. So the dx, the thickness of them, would be very, very small. So that was the step 1. So on step 2, we are going to say that the volume of the solid above R and below F is this one, is the integral from, so the integral means basically the sum of all the areas considering the thickness. So the volume of the small, the volume of very, very kind of thin boxes, okay? So it would be Sx dx, but we have to start at the very lowest value of x, which is far back in here. Let's call it, actually not this one, it should be this one, which is called x minimum, and the very largest value of x, which is very far front, like let's make it like this one, x maximum, right? So x min to x max, okay? So when we are going to do that, then in that case we get all the volume of this of the small boxes. Now in this step 3, we have what? Now let's basically look at each slices for a given x. For a given x, Sx is equal to what? Look at this slice Sx, okay? S of x, this one. Looking at this slice, what is changing is y. As you see in any slices, x is fixed, x is x not, but y is changing. So y is changing from the leftmost y, which we call it y mean, to the rightmost y, which is this y, we call it y max. Okay, so y is changing in each of the slices. So, and at any slice is basically the area of any slice is basically a two-dimensional area, okay? So this is just a simple integral, a single integral of fxy, and then y is changing, x is fixed, so x is a constant. X is constant, it's fixed, it's x naught in any of the slices. And it is from y mean to y max. Okay, great. Now if we look at the region R, look at the region R. What does it look like? Let me graph it. The region R, so let me have x-axis here, y-axis in here. Just assume the region R, which was down there on the xy plane. I'm gonna graph it separately. So the region R was something like this, okay? And then we just have one slice of the region R with x equals to x naught. Let me make it a little here. Okay, and then this was basically x equals to x naught. Okay, because that was the slice. So slice by the plane x equals to x naught parallel to y-axis, because y is changing and x is constant. Okay, and then and here we said that we're gonna start at the slice. We're gonna start at y mean. We go up to, let me just change this one a little. To y max in each slice. Y max. And then we are going to have each one of these slices like this, starting at x mean, which is the first slice, and then we go up to here, which is x max, and this is the last slice. Okay, so one note is that if I have my slice in here, then my bounds change. X was the same thing, but as you see, the y mean was somewhere in here and y max was somewhere in here. Okay, my bounds was changed if I take different slice. Therefore, I say that the double integral of fxy dA over the region R is what? Is which was what? Which was the volume of the solid above the region R, below the graph of f, and it was the integral of x mean to x max of Sx dx. And then we said that Sx itself is this integral. So I'm going to replace Sx by the integral of y mean to y max of f of x y and then dy and then dx. Okay, and something that you should be noticed is that the outer integral, the bounds, they're all numbers, but the inner bounds, these bounds, they could be functions of x. So they could be functions of x, because this is y equals to a function of x to y equals to a function of x. They could be functions or they could be constant, but the outer bounds, they all have to be numbers. Okay, this is called iterated integral. Okay, so let me show it to you everything together. So the double integral is the volume. To find the volume, we just take slices, then we find the area of each one of the slices, then we add up by taking the integral of all the slices, then we get this double integral. So it could be dy dx, or it could be dx dy. Basically by saying that if we just slice it with planes parallel to the y-axis, as the same as this one that we did in here, or parallel to the x-axis. Okay, so this is kind of like a brief idea of how to calculate double integrals. On the second lecture, we're gonna solve some examples, and then you're gonna see exactly how to do that.